Hey guys, we're discussing chapter 18, Magnetism. I've printed the notes here. These notes can be found in your Google Classroom. I'll post it up on your Google Classroom as soon as I upload the video. I will flip through it quite quickly, so if you need to pause the video at any time to catch up and see what I've written on the notes, please do so. So just have your notes handy before you start the video. Alright, so these are the things that I'll be covering in this video. Alright, what on earth are magnets? Alright, there are a few properties that we have to know about magnets. First and foremost, magnets attract magnetic material. So what on earth are magnetic materials? Magnetic materials are materials that can be used to make magnets. Consequently, non-magnetic materials are not attracted to magnets. The magnetic materials that you need to know, common ones: iron, nickel, cobalt, and steel. Alright, I used to help me remember, I need complete silence. INCS, iron, nickel, cobalt, and steel. Now, second property, magnets have two poles, and that the magnetic effect is strongest at these two poles. Alright, on top of that, the third property is that the freely suspended magnet will always come to rest in the north-south direction. Alright, the ancient Chinese discovered that certain iron ores will always come to rest in a certain direction. Alright, we now know them as lodestones, but the Chinese knew about magnetic effect for a long time. Because these stones will always point in the north-south direction, they decided I might as well suspend them in water, and bam, you have your very first compass created. Now, nomenclature. In a magnet, there's always one side that points to the North Pole. This is called the North Seeking Pole. Abbreviated, we call it the North Pole. Usually it's colored red, and it's always pointing to the North Pole, geographical North Pole of the Earth, where Santa lives. The other side, the South Seeking Pole, points to the South Pole, where penguins live, I guess. Now, the fourth property of magnets, just like electric charges, like poles repel and unlike poles attract. I got a bar magnet here, north-south. Got a neodymium magnet here. This is south. This is south, and this is north. Alright, north and south attract. If I put it the other way, flip it to the south side, south and south repel. Alright, so like poles repel, unlike poles attract. Alright, test for magnets. There's only one definitive test for identification of a magnet. Attraction is a poor test, because if I did not know that this is a neodymium magnet and this is just a normal paperclip with absolutely no magnetic properties at all, then I would not be able to tell which one is the magnet. Because if I put it like this, this attract. I put it the other way also, it will also attract. I swap over the poles, it will still attract. I swap the paperclip on this side, it will still attract. Now, I cannot have a definitive answer to whether this is the magnet or this one is the magnet. Now, a test for repulsion would tell me exactly whether it is a magnet or not. If I have a south pole here, I put a north pole here, attract. Still not a good definitive test. However, if I were to flip it over to the other side, where I have a south and south side, and it repels, then I definitely know that the two objects here that I have in my hands are magnets. Now, in an attraction situation, it's possible that I have a magnet, but it is also possible that I have a magnet and magnetic material. So therefore, I cannot definitively say that both of them are magnets. However, with a repulsion case, I can. Alright, please review this slide. Alright, we're finally talking about, next we're talking about magnetic induction. Alright, what is magnetic induction? If I were to place a paperclip with no magnetic properties on the south pole of a magnet, and consequently I decide to place another magnet, another paper clip on this side, you'll realize that actually this paper clip, which initially wasn't a magnet, is starting to act like a magnet and attracting it here. Now at this point where if I decide to remove it, this will lose its magnetism. Now the process through which the attraction occurs between a magnet and a non-magnet and a magnetic material is called magnetic induction. So what exactly is it? A magnetic induction is the process in which a magnetic material, such as this paper clip, becomes a magnet when it is near or in contact with a magnet. So it doesn't have to be in contact with a magnet for it to become a magnet. Now, why are objects attracted to a magnet? Is because when it is near a magnet, it itself becomes a magnet. But of course, it doesn't retain the magnetic properties for long for this paper clip. So we call this an induced magnet. Now, the side that is nearest to the south pole of the magnet will be induced oppositely with an opposite pole. So this side here will become a north and the opposite side will become a south. This now becomes an induced magnet. Now, because this is now a magnet, if I were to place a second paper clip here, in theory, it should now induce a north pole on this side. Sorry, let me transfer it. This is north, this is south. So because this is south over here, this will induce a north polarity on this side and you will attract. Alright, so that is induced magnetism. Now, just have a read at the question here. You can pause the video. Sorry for the cut, I'll just carry on. Alright, let's look at this example here. I have a similar example. I can show you. This post-it here is not a magnetic material. I can prove it to you. I have a neodymium magnet here. Doesn't attract. Alright, but if I were to place a paper clip on the other side, it will actually hold it in place. Now, induced magnetism, if you remember, does not require for the two objects to be in contact. They can be near each other and it will still work. So just to prove to you that this is really a non-magnetic material, I can push it away and it drops off. It's not stuck to the post-it. Now, another thing that is interesting to note is that when I have a bar magnet like this, sorry, I'll adjust so that it's in frame, north-south, and I put a paper clip over here, again, just from the rules that we learned from induced magnetism just in the previous slide, because this is the south pole here, this fella here, nearest to the south side, will be induced north, further away will be induced south. Since this is a north pole here, this fella here on this side of the paper clip, on the side, the paper clip nearest to the north side will be induced south, and this side north. Because they are north and south, if I bring them closer to one another, they will attract. Now, if I were to push this paper clip all the way to this side, then you realize that they will repel. Let me see whether I can get a better view of this. If this is a north pole here, that means the side closest to the pole north will be induced south, the side further away will be induced north, and therefore, because of them being north and light poles repelling one another, they will repel. So you can see that actually they don't want to stick. It moves away from one another. Alright, let's move on. We're going to talk about magnetization. Sorry, let's get in focus. Magnetization and demagnetization. Now, if I take this magnet here, a north and a south magnet, a north pole and south pole, if I cut it up into a few different pieces, they will still retain a north and south on each end of the pole. So basically, I created 3 individual smaller magnets. Now, if I were to cut this in turn into smaller and smaller pieces, they will still retain their magnetism. Now, if we carry on cutting them until they are small enough, we come to the concept of what we call magnetic domains. Now, these magnetic domains, also known as Weiss domains, determine whether an object is a magnet or not. If you have nice alignments, all these domains, magnetic domains, point in the same direction, then the object is a magnet. Alright, if you have random or no discernible alignment, the object is not a magnet. Sorry. Alright. Now, So if we can find a way, this is an unmagnetized bar, which is a magnetic material. If we can find a way to align all of these fellas together, then I would have created a magnet. So a paperclip by itself, all the small mini magnetic domains inside of it, they are all arranged randomly. As I bring a bar magnet close to it, this will cause all these domains to point in a certain direction, and this fella becomes, the paperclip becomes a magnet, and therefore attraction occurs. Of course, this only happens, this rotation and this alignment can only happen with magnetic materials. If I have a non-magnetic material such as the post-it, it's never going to happen. It will still remain as it is now. Therefore, this doesn't become an induced magnet, no attraction occurs. How does one magnetize or create a magnet? This is a paperclip. It's a magnetic material, but it's not a magnet. So I just prove it to you that it's not a magnet. There's no attraction. Nothing is happening with another paperclip. Now, you can make an object a magnet by stroking it. Now, the first method is called stroking. What you do is you take, if let's say I take the north side here, this is the north side of the magnet, and stroke it along the paperclip. Stroke it a few times. This will induce the alignment of all the domains inside. Now, importantly for you to note, if I use the north pole, I put it on the left side and I stroke it and I bring it all the way to the end here, the side that it lifts off will be induced oppositely. So if I use the north pole here, I stroke from left all the way to the right side of the clip will become a south pole. Alright, so just to show you that it has worked, and this is now a magnet, it should be able to lift up, when previously it could not lift up the paperclip. Now, how this works is that initially the paperclip was all randomly aligned. As I stroke the magnet along the paperclip, it causes all these little domains to be aligned until it becomes as such. And therefore, when it's all aligned, it is a magnet. Now, how do I get rid of the magnet? Because we learn about magnetizing, we need to learn how to demagnetize. These Wies domains, or the magnetic domains, can be gotten rid of. I can change the alignment of all these magnetic Wies domains by hitting it. I hit it hard enough or long enough, I impart enough energy to jar some of these fellas here out of alignment, and eventually it will stop being a magnet, because now this fella has all become randomly aligned. So I'll just test. Right, it's no longer able to attract. Now, another way you can get rid of the alignment, let me just induce here, stroke a few more times. Okay, let's just test whether this is a magnet now. Yes, it is. Another way for me to get rid of the alignment here is with a flame. Now, in thermal properties of matter, you learn that thermal energy at the molecular level is translated to kinetic energy. So, if I were to give it enough thermal energy to the paperclip, it will eventually lose its magnetism. Alright, so this fella initially was aligned, now it should be disaligned. So let's just test it out. Right, you don't see any more magnetic properties. So these are the two ways in which you can demagnetize, and the one way, stroking, in which you can magnetize. Of interest to note, alright, there are a few ways. You don't have to stroke it all the way like this. To magnetize an object, you can take the north pole and start from the center. Remember, the place where you last lift off, that will be induced oppositely. So if I use a north pole here, stroke halfway to the end, this side will be induced with a south. If I use a south pole to the center here and drag it all the way to the end, the place where it last lift off will be induced oppositely with this pole over here. So over here will be a north. Now, there are other ways for you to make a magnet. electrically, you can use electricity to induce magnetism, or rather to make magnetic materials a magnet. Now, current has been noticed by scientists to have a magnetic effect. Whenever they conduct a current experiment or electrical experiment, they start to see their compass start to point in different directions. So they realize that electricity has a magnetic effect and they can use it to make magnets. So typically they use a coil of wire and they put a magnetic material in the center. What this does is that this object here, the magnetic material with random alignment, will have all their magnetic domains aligned in a certain direction. Now, how do I tell whether an object, which pole is being induced? We use something called the right hand grip rule, or rather which pole the object will end up with. Now, I have a coil here. So if an object, if I attach the battery in such a way that the current flows from here all the way to here. So you can see that the current flows here, here, and here. So it flows from the front to the back. We use something called the right hand grip rule. Let me focus out a bit. I use something called the right hand grip rule because the current will flow in this direction. Right hand grip rule, it flows from the front to the back. Where my thumb is pointing, that's where the North Pole is. Alright, if I allow the current to flow from here from this point here to this point here, current flows from the front to the back, to the front to the back. I use the right hand grip. My fingers follow the direction of the current. My thumb, with the thumbs up sign, this shows the direction of the North Pole. Alright, this method is called the right hand grip rule. So curl the fingers in the direction of the current flow, your thumb points to the direction of the North Pole. Another way you can do this is to look at an object. Let me adjust the camera a little bit. Now, if I have current flowing from here to here, you can see that the current is flowing in this direction. Now, if I were to rotate it and point it like this, you can see that the pen is moving in an anti-clockwise direction. So if it's an anti-clockwise direction, this side here, if you look at it, this side here is the North Pole. If I put it here and the current flows in this direction, so the current flows in this direction. If I were to put it here, you realize that the pencil is moving in a clockwise direction. So if this is a clockwise direction, the side that you are looking at becomes the South Pole. Alright, anti-clockwise, if you look at it, then the side you are looking from becomes the North Pole. If you look at it and it's a clockwise direction, the side you are looking at from is actually the South Pole. Alright, so we talked about magnetization. Just now I already talked about demagnetizing, and the main idea is that you want to cause the perfectly aligned magnetic domains to point now in random directions. And you do this by imparting energy, either by heating or hammering. Now, another way that you can do this is to use electricity and using an AC current. So how is this done? Because when you use a DC current and the current flows in a certain way, it causes all the magnetic domains to point in one direction. Now, what exactly is alternating current? Alternating current means that the current alternates direction hundreds and thousands of times every second. So it will flow in this direction, then the next second it will flow. Flow this way, flow that way, flow this way, flow that way. So what that happens to the magnetic domains inside, because when the current is flowing in this direction, it will align here. When it's flowing in the other direction, it will align to the other side. So it will point here and it will point there. It will point to the left, it will point to the right, it will point to the left, it will point to the right. So if you use AC through a coil and you align this in the east-west direction, I'll tell you why you need to align this in the east-west direction, and you slowly pull it out. This portion of the magnetic material that is no longer under the influence of the coil, it will be stuck in whatever alignment that it was. So it was rotating left, right, left, right, left, right because of the alternating current. So when the moment I pull it out, it will freeze there. So the second I pull it out, the next portion, this portion now, maybe it's in this direction. So as I slowly pull it out, what you have is that all the magnetic materials here, the magnetic domains will be in random directions. So I slowly pull it out, bring this fellow far away, then I have demagnetized the magnetic material. Why is it important to do this in the east-west direction? Because if I do this in the north-south direction, I pull it out, there's a higher possibility of this magnetic domain aligning with the Earth's natural magnetic field. So instead of having a no magnet, you may create a very weak magnet because of the Earth's dormant magnetic field. Talking about magnetic fields, we move on to the next section. Magnetic fields is a region surrounding a magnet in which a body experiences, a magnetic material experiences a magnetic force. So if I have a magnet here, I bring the object closer and closer and closer, it's still not feeling any magnetic force. I say it's out of the magnetic field. I bring it closer and closer and closer. The point it gets attracted, that's the magnetic field of this magnet here. So if I draw a circle around the magnetic field, is as such. Now, magnetic fields can be shown just like electric fields using magnetic lines of force. Now, if I draw a few magnetic lines of force, then what I have is a magnetic field pattern. Alright, I won't talk so much because magnetic field patterns are pretty much similar to electric fields, but if I have a magnet, north and south here, if I have a mini compass here, the compass will align itself in a certain direction. So I draw the arrow here, I take the compass, I put it back over here, I will get a slightly different direction. So if I carry on doing this, eventually you have this. And then if I connect all the lines together, I have a magnetic field line. Alright, so this is how you can draw magnetic field patterns or find out the magnetic field pattern of a magnet using just a compass. Now, a few things for you to take note. One, magnetic field lines move out from the north and go into the south. They do not cross and intersect, similar to electric field lines. Field lines are drawn closer. When the field lines are closer, it indicates a stronger field. Now, if you refer to slide 5, magnets are strongest at their poles. That's why you see here, magnets are strongest at the poles. That's why you see here the field lines here are more dense as compared to over here. Alright. Magnetic field lines look very similar to a positive and negative field line, or a negative negative and a positive positive field line for electric fields. Alright, so I don't want to explain and elaborate too much, just revise on your static electricity. Now, what is unique is that magnetic field lines can be changed. Alright, there are certain equipment, and we use this concept in magnetic shielding. Magnetic shielding is for equipment which are sensitive to magnetic field, so I do not want to expose them to any magnetic field. So if let's say I have a north and south pole here and the field lines are typically shown like that, if I want to place an object in the center here and this object is sensitive to magnetic fields, I will have to do something. If I put a magnetic material around here, then the magnetic field lines will preferably go through the magnetic material. So if I were to place an object like this, a magnetic material, the field lines which by right should go through here will actually preferably go through here and then exit out here. Alright, so practically that means I do not have any field lines in the center here, and this region is free of field lines and I can place my sensitive equipment here. Alternatively, if I have a pole like this, a north-south, and I want to place my object, a sensitive object over here, I can place my magnetic material over here. what happens? The field lines go here. Instead of going through, they will preferably go through here and then out. The same with these field lines here, preferably go through here and then out. So what you have is an area free of magnetic field lines and magnetic effect, and therefore safe for sensitive equipment. Now, magnetic keepers. I talked about the domains before, so just a reminder. Alright, if I have a magnet that is aligned, if I have the domains aligned, then I have a magnet. But the tendency for near the free ends of the magnet is that they will start to repel one another. So these fellas here will start pointing to the left, these fellas here will start pointing to the right. Practically what that means is that my magnet will get weaker over time because now it is losing its alignment. These fellas are not all pointing in one direction, but they are moving away. Now, magnetic keepers, what they are magnetic objects that place here in this configuration. This is a magnet, this is a magnet, these are the two keepers here. So what that does is that the magnetic domains will preferably point in a certain direction like that. So you retain the magnetism for a much longer time. So that's why it's called a magnetic keeper. Alright, I'll skip past this, you can read this for yourself. I'll skip past this as well, electric field lines, the Earth's magnetic field. And we'll move on to comparing magnetic materials. Now, if I have an iron material and a steel material here, and I place a magnet here, this iron and steel becomes induced magnets. Now, what is noticed is that iron will attract more of the paper clips, while the steel will attract less. So what it means practically is that the iron is a stronger induced magnet, while the steel is a weaker induced magnet. When I remove the object, what is noticed is that the iron will drop all of the paper clip while the steel retains. Now, this means that there are differences between the magnetic materials. So we classify them according to this table here. Soft magnetic materials, such as iron, they magnetize easily but also demagnetize easily, while hard magnetic materials such as steel, alnico and neodymium, the one that I have here, they are difficult to magnetize, but at the same time they are also difficult to demagnetize. So functionally, I will use hard magnetic materials for permanent magnets and soft for temporary magnets. Now, uses permanent magnets, the magnetic door catch in your fridge. Alright, there's a magnet there, you close it, it will keep it and seal it tight. Your door catches also work the same way, and compasses. All these require a permanent magnet, because if they are not permanent, then and it loses its magnetism easily, then your door cannot close properly, your door catch cannot be held properly, your compass will point in any direction. So temporary magnets are used in applications where I do not want the magnetic fields to be permanent. So we use, if you remember, electromagnets, the induction of the making of magnetic materials into magnets using electricity. Electromagnets are objects that become magnet due to electricity. Alright, we use some in the scrapyard to attract all the metals. The question is, why not use hard magnetic materials here? Because then if I were to already attract some of these materials here, and this is a hard magnetic material, it will be difficult for you to drop all the metals once you have shifted over to the other side. Another use of temporary magnets is ATM cards. If you have ATM cards here, right, this is mine, you can see Azhar here. Alright, if you have magnetic cards, credit cards or ATM cards, you notice at the back you have a black strip. So this black strip here is a magnetic strip. These magnetic strips are aligned, the domains in this strip are aligned in a certain way, so that when you swipe it, or the cashier swipes it in the machine, it will register the magnetic field and it will say that it's your card, enter your PIN, and as long as everything matches up, then you can use the card. Now, you can spoil this by taking a very strong magnet such as a neodymium magnet, putting it across the black color part and pull it. What this does, it causes the magnetic domains to align in a certain way, not in the original way that it was set up to be, and this card now is no longer usable. Alright? The old TVs also use temporary magnets. The old CRT TVs, the big fat ones, not the small slim ones that you have now, have an electron gun near the back of the TV. So what it does is that when the electron hit the TV, it lights up a certain color and that forms 1 pixel. So in the TV, you have these magnetic electromagnets for which you can control the strength of and control the attraction of the electrons, so that the electrons can move here, or can move left and right on the TV, and that will create your image. Electric bells, we cover this more in electromagnetism. And lastly, moving coil loudspeakers, temporary magnets and permanent magnets. This uses a combination of temporary and permanent magnet. So as you know, a loudspeaker is basically a cone, and the cone moving left and right, disturbing the air particles, and finally reaching your ear is what you hear as sound, or the music you hear coming out from your speaker. So now, how do I cause this cone to move in and out, or left and right in this manner? I have a permanent magnet here, and I have an electromagnet over here. The electromagnet, using a coil and a piece of magnetic material connected to the outlet, when electricity flows through it, it will become a magnet. Now, I can control the direction and the flow of the electricity flowing through this, so that it can become a north or it can become a south here, which will attract or repel. So this fella will move in and out based on the electrical signals here, and you create sound. Alright, that's it from me. That's the end of the chapter. I think it'll be about a half an hour video. I hope it helps you in your studies. Please refer to it. Thank you. Have a good holiday.